Hi everyone, how are you doing? Hello Abhishek. Hi Devesh. Hi Kavya. Hi Aditya. Hi Pankaj. Hello Abhishek. Okay, hello Deep. So now let's just get started, right? So before I start a new topic, which is very exciting and very important also, not just exciting, this is very important also. But before I start a new topic, just let us just refresh, earlier the last class topic, and in particular, let's just solve some good questions here. Okay. So can you solve this question? Just try to solve this question and let me know what is the answer you're getting. This question has been asked in IIT JAM. So there is an examination IIT JAM, right? So I think this is for MSc. For MSc there is an examination IIT JAM. That question has been asked in IIT JAM mathematics. MA means mathematics. Okay. So this is a standard question only. So just let me know what is the answer you're getting. They are saying that consider some subspace such that it is of 10 dimensional space. Okay, sorry, not 10 dimensional space, I mean the vector is are the 10 dimensional here. Okay, they're asking the dimension itself. So now they are saying that that xn, which means if you are saying this is x1, this is x2, like that, right? This is x10. So every xn is nothing but summation of above 2. If n is greater than or equal to 3, right? So which means you can say that for x1 there is nothing above, right? I mean x for x1 x2, let's suppose this is a and b. But for x3, okay, for n greater than or equal to 3, for x3 it is summation of above 2, so it is a plus b. For x4, I think it will be a plus 2b, right? For x5, I think it will be, okay. Can you write it? So let me write it, the whole thing. It will be a plus b, a plus b plus b, right? A plus b plus b, and then it will be a plus 2b plus, I think, a plus b, something like that, right? And so on, right? And so on. So basically, there will be, you can say there will be this kind of vectors, basically, right? In that particular space. Now, if you try to solve this, okay, then if you decompose this, then it will be of how much vectors will be, how many vectors will be in the decomposition? How many linearly independent vectors will be there in the decomposition? If you try to decompose this, okay, so it will be two, right? So decomposition, let me write the decomposition itself. So this will be equal to, okay, this will be equal to, the decomposition will look like this, equal to a into something plus b into something, right? I mean, I'm not very much interested to solve like what it will get, but I think this is clear to everyone that we will be getting two vectors here, right? Is this fine? That in the decomposition we will be getting two vectors. Okay. See, this question is from IIT JAM. Okay. This is a good question. So that's why I've taken this question. I hope you understood. And that is why, since we are getting this kind of decomposition, that is why you can say dimension of this vector space is how much? Is this 10? No, right? It is 2, right? 2. Because two linearly independent vectors, right? Okay. Let me know how many of you are comfortable with this explanation. If there is any confusion, any doubt, you can just let me know. Okay. Okay. I hope that is fine, right? Great. Now let's just solve this question. This is MSQ question, which is again asked in IIT JAM, okay, mathematics examination. So let's just solve this question. So what they're saying that you have this kind of vector space for which of the following, this is two-dimensional subspace, okay. So they are saying if you are having this kind of vector space, so for which of the following it is two-dimensional subspace. For two-dimensional subspace, what do you need? What are the things that you need? See, let's suppose it is non-homogeneous. Let's suppose this gamma is not zero. Let's suppose gamma is one. Can it be the vector space first of all? Okay. For gamma equal to one, it is non-homogeneous, right? So it cannot be the vector space at the first place. So it cannot. The solutions will not form the vector space at the first place, right? So you can say the solution will not form a vector space at first place. Okay. Is this fine to everyone? So basically, gamma equal to 1 is not possible. Hence, can I say directly that B is not the answer? Let me know. Okay. So B is not the answer. I hope you understood why this is not the answer. Okay. Cool. Now let's just move to let's just see that what can be the answer. So if you want, you can do one thing. You can write it like this. See, you can write like this, that this is solution of some. So gamma has to be 0. So this should be the solution of alpha, beta, 1, and gamma has to be 0, right? A B. So this is, you can say, this is A B, which we call. Do everyone know what we call this? Augmented matrix, right? We call this augmented matrix. Do you remember this? Okay, we call this augmented matrix. So let's just see that how to solve for this augmented matrix. Can you tell me? Can you tell me if you want two-dimensional space, then how many free variables you need in the solution? How many free variables you need if you want two-dimensional space? So my question is that, see, I'm just asking you a simple question. Okay. Okay, you can just let me know if my speed is too much. Am I teaching the things? I mean, in too fast or too slow? You can just let me know. Is this too fast? Slow is okay. I mean, actually, I do not much care about the slow, but I care about the fast. So just let me know if it is very fast. Okay, if it is slow, then it might be slow for you actually, but it might not be slow for other person. Okay. Okay, okay. So now what I'm saying here is that if you have something like this, then you want the solutions, right? You want the solutions of this such that solution such that solution has two linearly independent vectors, right? So it means what? Number of, can anyone tell me number of pivot pivots or number of free? Can anyone tell me number of free? If you want two linearly independent, I think you need two free or you need one free. Tell me. I think you need two free, right? Okay. And pivot column should be one. Okay. So this is the I mean objective that we want to achieve. Now, if you want just one pivot and exactly one pivot and exactly two free columns, I mean automatically it will be two free columns. So if you want exactly one pivot, okay, tell me, can this alpha and beta both be zero? Can this alpha and beta both be zero and still exactly one pivot? Tell me, is this possible? Yes, right. So alpha beta both can be zero. Still, this will be the pivot, right? This will be the pivot. So you can say that for this alpha and beta, let's suppose you have four possibilities, right? Okay. So you just tell me, can this alpha beta both be zero? Then answer is yes, it is possible. I mean, here you will be getting one pivot, right? Here you will be getting one pivot. Can the alpha be zero and beta be one? How many pivots it will be? Actually, you will be getting one pivot. Whatever is the value of alpha and beta, you will be getting always one pivot, isn't it? Does it really depend on the value of alpha beta? Tell me. See, how many rows you have? One row, isn't it? You have one row, and this is a non-zero. I mean, this is anyway. In worst case, it will be the pivot. Okay, either alpha will be the pivot or beta will be the pivot. If nothing worse, then one will be the pivot, right? So if you have just one row, then number of the pivots cannot be more than one. Okay. So it is zero only when the row is zero. So since the row is not zero, that's why number of pivots will always be one, irrespective of the value of alpha and beta. Tell me, is this okay to everyone? See, what I'm trying to say here is that here, if the alpha is zero, then this will the pivot. If see here, if this is the augmented matrix that you have, alpha, beta, one and zero, right? Then if alpha is zero, then what is the pivot? And beta is not zero. Then pivot is Let's suppose I call it X, I call it Y, I call it Z. Then pivot is second column, right? Which is Y, right? Similarly, you know the answers, right? So for every other thing, you know the answer. If alpha is 0, beta is 0, then pivot is Z, and so on, right? So you can say always, always exactly one pivot, right? One pivot, irrespective of value of alpha and beta. So hence, we only care about the gamma. Whatever is the value of alpha and beta doesn't really matter to me, right? So you can say, what is the answer here? Yeah. So A is the answer, C is the answer, D is the answer. Okay. A, C, D is the correct answer. Understood? So let me just copy this question. Okay. So here we are getting, sorry, A, C, and D. Let's just see the answers. Okay. I think answer screenshot I don't have, but that's fine. Okay. So ACD is the answer. Understood? Okay. Some of the people said, I think A and C. They have not said D. So now you understood, right? Now you understood that D is also the answer. Okay. Now let's see this question. I think this question has been asked in GATE DA recently in 2024. So let's just see this question. What they're saying. Select all the choices of subspace of R3. Okay. So this is the question that they're asking. This is MSQ question. Let's just see that which of the following is subspace of R3. Is this A subspace of R3? What do you think? This is the linear combination of two vectors. I think A is the subspace of R3. Okay. Everyone understood that A is the subspace of R3. Why it is subspace of R3? Because it is a linear combination of all the these are the all the linear combinations. Okay. So you don't need to think anything. These are the all linear combinations. So since these are the all linear combinations, that's why this is the answer. Okay. So you can say, maybe I can just write it that, okay, all linear combinations. Okay. What about this option B? Okay. Some of the people are saying no. Can you tell me the reason why no? Can anyone tell me the reason? Aditya is saying negative linear combination is not there. What do you mean by negative? Why you even need negative? I mean, uh, it's fine, right? I mean, you have alpha square and something. I mean, I haven't understood actually. I mean, your answer, whatever you said. So basically, this is something that we have, right? Now let's just analyze this. Okay, let's just analyze this very carefully. That if this B is the answer or not. Let's just analyze this. No, I think zero is there. Is zero is a problem here? Do you think zero is not there in this space? Okay, so zero is included, right? Now let's just check whether it is close. See, only two things you need to check. Although there are multiple, properties like u plus v equal to v plus u or something like that. Do you remember those list of properties? But you never need to check those. Okay, so only just check whether the zero is included, and the second thing is that it is closed or not. Okay, closed or not, closed under addition basically. Okay, I mean, uh, basically, which means if you take, let's suppose, two vectors from here. Okay, can you give me one vector from this space? Maybe let's just take alpha equal to 1, beta equal to. So let's just take one vector from this space, which will be 1 into 1 to 0 plus 1 into 1 0 1. Is this fine to everyone? Now let's just take maybe one more vector. Okay, let's just take one more vector. Alpha equal to maybe -1, beta equal to -1. Okay. I mean, the vector will be same, but that's fine, I think, for the another value of alpha and beta. Or maybe you can take the same vector, doesn't really matter. Okay. So let's just take another vector for this alpha and beta for these values. Okay. Is this fine? I mean, the vector is same. That's really okay. That's fine. Okay. Or maybe if you're really confused, I can do one thing. Let's just take only one vector here. Okay. Let's just take only one vector. Is this fine? At least is this fine that you have one vector this? Tell me. Okay. Okay. Now should we close under addition and multiplication basically? Okay. You can say actually these both boil down to the same thing, but still and multiplication. What do you mean by that? Let's suppose this vector is there. Now you multiply by any scalar here. Okay. Let's suppose C is any scalar here. You multiply. Then don't you think that C into this vector should also be in the part of the space? If this is the vector space, which means let's just multiply by 2. Okay. Then what you will be getting? Tell me. What you will be getting is, I think, something like this. Right? Is this vector part of this space? Tell me. Can you represent any real number? Okay, real number as if I mean alpha and beta has to be the real numbers. Okay. Can you represent? Yeah, I think square root of 2 is real number. Okay, that's fine. Okay. Yeah. Yeah. So I'm coming to that point. So basically, I mean, that's okay. So now I multiplied by 2, and it seems like that it is also the part of the space. That's fine. Now, let's just do one thing. Let's just do one thing. Let's just multiply. Okay. Let's just multiply y, let's suppose, minus 1. Okay. Let's just multiply by minus 1. Then it will be minus 1 into this, isn't it? If you multiply by minus 1, then you will be getting this. Is this fine? See, multiplication by 2 we did. Now I'm just checking if we multiply by minus 1, then we will be getting this. Now tell me, is this vector a part of this space? What do you think? No, right? Because alpha square is minus 1 and alpha cannot be any, I mean, alpha is imaginary basically. So any real number square cannot be minus 1, right? So that's why it is not closed under the multiplication, which means you picked one of the vector from here, you multiply it by minus 1 or you multiply by any other scalar. Okay. I mean, any other negative number for the sake of the counter example. Okay. And we found out that it is not closed under multiplication. Is this fine? Understood, right? Okay. So that is why it is not the vector space. See, you can also understand intuitively that it is the linear combination of only the positive or you can say the only the perfect square numbers or something like that. Okay. If not even perfect square, you can say it is the multiplication. It is the addition or the linear combination using only the positive coefficients. Okay. It is not all linear combinations. If it is not all linear combinations, somewhere it will be the problem. Okay. So it is, you can say it is linear combination of linear combination using positive coefficients, right? You can say it is linear combination using using positive coefficient. Okay. It is not linear combination of all coefficients. It is not linear combination Okay. So that's why it is not a vector space. Understood? So basically, what we did to check whether it is a vector space or not, we picked one of the vector here. Okay, maybe by putting alpha one and beta one, we took one of the vector here. Okay, or maybe you can just pick this vector. Okay, by putting beta equal to 0 and alpha equal to 1. Just you pick one this vector, and then you multiply by the scalar. Okay, it is your choice to multiply by any scalar. Then you multiply the scalar. Let's suppose -1 and and after multiplication you found out it is not the part of this space, right? So that's why it is not the vector space. Let me know if you have understood this or not. How many of you have understood? So I can say this B, it is not the vector space. Okay. Is there anyone who like to answer this on the gator flow? I'm not sure that how good or bad answer it is there on the gator flow. But do you want to answer this? Anyone wants to answer this question on the gator flow? Anyone? Okay, Aditya is saying yes. So Aditya and Abhishek, you both answer, okay, your own versions, just based on this explanation, whatever we decide. Okay, you both answered that. Okay, you picked one of the vector and did the scalar multiplication, and why this is the vector space, why this is not the vector space. And then let's just see this. This is the set of homogeneous equations. Okay, the set of homogeneous solution of the set of homogeneous equations. Tell me, what do you think? So this is, you can see, solution of, if it is a homogeneous equation solution, do you really think it will be any problem? I think it will be the subspace, right? This is not the subspace, but this is subspace. Okay, or it is a vector space, right? What about this? Is this a homogeneous? Is this homogeneous? This is 4 here. So actually it is non-homogeneous, right? It is non-homogeneous. If it is non-homogeneous, will it be the vector space? What do you think? No, right? No. So it will be not be the vector space. Okay. Because there will be the constant vector that we have already seen in the previous lectures also. Okay. Let me know if there is any confusion till now. Is this fine? So this question has been asked recently. I hope all of you understood that why A and C are the correct options, why B and D are not the correct options, right? Okay. Now let's just see this. This question, okay, sorry, this is the same question. Let's just move further. Yeah, here it was A, C, D was the answer, right? I mean, B was not the answer. A, C, D. These are the answers, right? Let's just see this question. Which of the following are the subspace of R3? Do you want to solve this question as a homework? Okay. Answer, okay. Answer is on the next page. Okay. Answer on the next page with the explanation. Okay. So answer and the explanation on the next page. Just take it as a homework. Is this fine to everyone? Okay. Now let's just see this question. What they're saying, if V1 to Vn generate a span vector space, then V1 to Vn necessarily linearly independent. Okay, tell me. If it is spanning, then no, right? This is no. This may be linearly dependent. Why? Because maybe you can say, okay, this 1, 2, and maybe 2, 3. Maybe you can have 1, 4 also, right? Or maybe 2, 4. Sorry, you can have 2, 4 also. So this also span R2, but not linearly independent. What can you say about the dimension of V? Can you say it will be less than equal to n, greater than equal to n, or something like that? Any claim that you can make? Yes. Anuvesh Kumar and Aditya has given correct answer, I think. Right? They are saying less than equal to n. Anyone who agree with that? Less than equal to n? Yes. Pankaj is also saying less than equal to n, right? Okay, great. So the answer is less than equal to n. And I hope you understood that why this is the answer, right? So anyone who is having problem in understanding this, that why less than equal to n should be there, dimension should be less than equal to n, because basis will be obviously lesser than equal to n, right? Okay, it may be linearly dependent, and basis will be, I mean, part of this. Okay, some part of this. So you can say, yeah, dimension of b is less than equal to n, right? See, understood? If there is any problem, you can just let me know. By the way, this question I have taken from Berkeley University. Let's just see another question from Berkeley University. It is also a good question, a true false question. If W is subspace of V and B is a basis of 4B, yeah, this is not just good question. This is very tricky, I can say. Okay, this is very tricky. What is your answer here? It seems true, but can it be false or something like that? Okay, this is very tricky question actually. So what they're saying, that you have some subspace of V. Let's take the example of R2 itself. Okay, let's take the example of R2 itself. Tell me, is this line subspace of R2? This is subspace of R2. This line could be anything. Okay, let's just assume that this line is k into 1 into 1. Okay, this line could be anything, and definitely it is a subspace of R2. Can you tell me the basis for this subspace? 1 1, right? 1 1. So this is the basis for this subspace. Now let's just talk about any random basis. Okay, so let B be the any basis. Okay, some basis for B. Let's just say that B is some basis uh for the R2. Okay, this could be the standard basis also, right? Okay, and this is the basis for, you can say this is the basis for subspace, and this is the basis for R2. Tell me, is this a subset? Is this basis a subset? What do you think? So see, there is some basis, and now the subspace is basically subspace need not to be. I mean, you can make this subspace. Okay, whatever is the subspace. Okay, see, whatever the subspace is, can you form this subspace? Okay, any vector in the subspace using this? Tell me, using this, using these two vectors, can you do? So, so we can definitely get any vector in the subspace using these two vectors. With the support of these two vectors, we can get any vector in the subspace. But let's suppose I say you just pick one vector, or maybe some subset of this. Is this really necessary that you can still fill this space? No. Okay, that's really very tricky question. Okay, so I know it might be not very intuitive to all of you. To be honest, it was not intuitive for me also. Okay, when I first saw this question, I said, oh, true. Okay, it should be true or something like that. I mean, initially at the first thought process, it seems like it is true. Now, actually, it is false. Even at the Berkeley University, okay, I have taken this screenshot from their answer itself. They are saying it is false. They are also saying this is also very tricky. This got me too. Okay, so professor is also saying that this got me too. So means most probably the professor at the first sight, and he might be thinking that okay, it is true. Actually, I also thought it is true. Okay, at the first sight, I also thought it is true. So it this question got professor too. So obviously it is very okay, okay, very much okay. Don't judge yourself that okay, why you were not able to solve the question. Don't worry about it. Okay. But yeah, this question is very very tricky. I hope you are understanding. Let me just try to make this more more explainable. So basically, what I'm trying to say, you can fill this subspace using the basis of R2, that's for sure. But the interestingly, if you take just sum of the vector from R2, of sum of the vector from this basis, okay, if you take just sum of the vector from this basis, it need not to fill this space, okay. See, using these two vectors, you can fill the space, but just one or two vectors, maybe, I mean, just subset may not be able to fill. Okay, is this okay to everyone? See, in the answer also, what they are saying a counter example they are giving of R3, I think. Okay, and they are they are taking some line in R3, right? Now they are saying if the statement was true, then one of the vectors in V would be the basis for W. Okay, just one of the vector. Okay, just one of the vector, two of the vectors. But this is bogus. Okay, so basically all of these three can fill this subspace. Obviously, all of these three can do anything in R3. Okay, can get any vector in R3, but just one alone can't do anything. Okay, I mean, can't do much things. Understood? Okay. Now let's just start a new topic, which is column space and null space. It is very very interesting, very very important also. So let me just say it is column space and null space of a matrix A. I mean, these spaces are defined for some matrix A, which means I will give you a matrix A. I will ask you what is the column space of this matrix. What is null space of this matrix? These type of questions I will be asking you. Okay. So by the way, these will be the subspaces only. So these column space and null space are also the vector space or the subspace. But let's just see that what are these and why we even need it. Okay, we will also see that what is so special that we are seeing these subspaces as a different topic, which means that okay, first of all we will define what is a column space, what is a null space, and we will also see their importance. That why this is so important. I will tell you that. Okay. You know what? There was one interview of Gilbert Stein. Professor Gilbert Stein from MIT. Though, like he recently got retired. And in that interview, the interviewer asked Gilbert Stein. Recently, that interview happened, I think, 1 or 2 years ago. That what is your most favorite topic of linear algebra? So he has spent. Let me just tell you, he has spent 60+ years in linear algebra. 60+ years, too much, right? Not a joke. That too at MIT, 60+ years at MIT. And someone asked him, okay, I will tell you the YouTube video link also. This is just, I think, 5-minute video. Okay, 5-minute video link. I will also tell you. Someone asked him that what is your most favorite topic of linear algebra, and then what he replied. Remember, he's Gilbert Strang, Professor Gilbert Strang. What he replied? This. Okay. So this is most favorite topic of Gilbert Stein. So now you imagine the importance of this topic. Okay. It is not just favorite because it might seem fancy. It must be having very, 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 very much significance in linear algebra. That is the only reason Professor Gilbert Stein said that it is the most favorite topic of him. Okay, so we will see these topics in very much good detail because this is extremely necessary to understand linear algebra. Okay, so let's just start with the very very important topic, which is column space and null space. Right, I will tell you this 5-minute video link. Okay, currently I don't have, but I will definitely tell you. It is just a 5-minute video, and the Professor Gilbert Stein himself said that it is his most favorite topic of linear algebra. Okay, so let's just define what is column space. Okay, so basically the column space is nothing but let's suppose that by the way, these column space and null space are defined for a matrix A. Okay, if it is a matrix, then I will talk about column space and null space. So let's suppose that A is a matrix who is having the columns A1 to AN. For example, for example, this is A1, this is A2. Okay. Let's suppose this is the matrix whose columns are even to n. Then column space is very easy to easy by definition. Also for other purpose also it is very easy. It is just a span of all these vectors. It's a span of all the column vectors. This is the column space. Understood? Okay. Okay. Let's just see more things about the column space and null space. So let me first define it, by the definition, and then we will see the questions. So by the way, the definition is clear to everyone that whatever space that these vectors are spanning, this is the column space, isn't it? Now, what is null space? Null space is nothing but if we have a matrix A, okay, let's suppose this is the matrix A, and there is a vector X, okay, there is a vector X that makes this matrix 0. Then we say that X, those such X are in null space. Okay. Any vector that make this matrix 0 is in null space. Can I say that this statement, just tell me, can I say this statement, first of all, tell me this is true or false, that 0, uh, 0 vector, as in vector, I want to write it. So 0 is always in null space. Is this true? What do you think? Yes, this is trivial statement. This is true, right? This is true. Okay. Okay. So we will see that why these column spaces and null spaces are important. But a null space of A is X such that Ax equal to 0. Okay. Now let's just see why. Okay, I will tell you that why this column space and null space matter to us. It is actually very important. We will see that why it matter to us. But before that, let's just see some numerical question where we find out the column space, where we find out the null space, these kind of things. Okay. So let's just see this question. Which of the following vectors are in null space of matrix A? Select all that apply. Okay, just solve this question. This is MSQ question which I have directly taken from this university. Obviously, 0 must be there, right? I think dimension itself doesn't match. I think this dimension itself doesn't match if you multiply 1, 2. Okay, sorry. This is 2 into 2 rows and 4 columns. Okay, sorry. The 0 is not there. I'm sorry about it. Dimension should be 4. Okay, so yeah, here A and C dimension doesn't match. Okay, A and C dimension doesn't match. Let's just see the dimension of B and D. I mean the dimension at least match because this is 2 into 4, so it should be 4 into 1, right? So just tell me, if you multiply these two vector, this vector with this matrix, will you be getting 0? I think -4 multiply by -4 and then -1 here. This will be -9 and then +1, right? -4, 8, 8 which are 12 and this 12. I think B is the answer. What about this? What about this? What about D? You just, okay, I don't think it is the answer. You multiply by 1 and -1, so it will be giving you, I think, -7 and then 9. It is not the answer, right? So I think only B is the answer here. Okay, so you can check with the multiplication, right? So which means you can check that 1, 5, 8, 9, 2, 4, 10, 12 multiplied by -4, -1, 0, 1. It is giving you 0, right? But this is not giving you 0. So that is why B is the correct answer here. Okay. Can you solve this question as an homework? This particular question, can you solve this question as an homework? Easy question, same type, but easy question. Okay. Okay, just give me a moment. Okay, so D is the answer here, right? Okay, great. So yeah, D is the answer. Let's just check. I think I don't have the answers, but yeah, this is easy question. So D is the answer. Great. Now let's just see this example, what they are trying to say. So every solution of this into this equal to zero is a form of, if you try to solve this, then you will be getting minus y into y. Okay. So you will be getting, I mean, this is set of homogeneous equations. You can solve it. It will be k into, you can say it is k into uh, minus 1 and 1. Okay. For some k, right? So this is the line. So basically, you can say that null space is this, right? Null space is this. So what do I mean to say is something like this. See here. Suppose I ask you what is the null space of this matrix. Okay. So now let's just see that how to compute the entire null space. Okay. I mean, you have already done it, but done it in the previous classes, but the null space term was not there. So my question is that how to find entire null space. See, is this vector entire null space? No, right? It is just a one of the vector from the null space, right? It is just one of the vector from the null space. But my question is that how to find entire null space. Okay. So very, very easy. If this is the matrix A, then how to find? Solve Ax equal to 0. That's all, right? Solve Ax equal to 0. So if you solve Ax equal to 0, what you will be getting here? If you solve this 1 1 0 0, what you will be getting? I think this is the free variable. Okay. So you can say that x plus y equal to 0 is there, and y is equal to k, right? So x equal to minus k, and then from here you will be getting x equal to minus k. So I think it is very easy, k into minus 1 1, right? So this is the solution that you are getting here. Now if you since you have got something like this, so if you multiply with this x to this a, what you will be getting? 0, right? 0. So you can say this is the null space. Okay, this is the null space. Or in other words, can I say something like this? Okay, either you say like this or doesn't really matter. Okay, you can also say something like this, where null space null space is equal to span of span of this vector, right? Minus 1 1. Understood? This is the null space. So basically, how to find the entire null space? The solution of Ax equal to 0 is just a entire null space. Okay, very, very easy. Let's just see. Let's just see these questions. Can you find the basis for this null space? Just let me know. Can you find the basis for this null space? Just solve Ax equal to 0 and let me know. Okay. Okay. So let's just see. Let's just see what is the null space for this, right? Let's just see. If you solve, yeah, I think these are linearly independent vectors. So this is the, yeah, you need to convert that to the row echelon form, maybe. Yeah, okay. So maybe I think, okay, I don't have the answer here, but let's just quickly do it. Maybe I think you can do this. R2, you can replace this R2y, maybe R1 minus R2 or something like this. Is this fine? Okay. So it will be something like this, 1 1 0 and you are replacing, or r2 minus r1 doesn't really matter. If you are comfortable with the r2 minus r1, you can do this. Okay, so it will be 110, and then r2 minus r1, 0 minus 1 and 1, then 0 1 1. So now this is okay, this is not okay, so you can replace r3 by r3 plus r2. So if you replace it, what you will be getting? You will be getting 1 1 0 0 minus 1 1, and then if you add both, 0 0, isn't it? So this is okay, and this is okay, and this is also pivot. So I think these are linearly independent vectors. So that's fine. I mean, there is no free variable here. So what is the solution of x equal to 0? Yeah. So since there is no free variable, so x equal to 0, you will say it is linearly independent. So x equal to 0 is the only, you can say, the solution. So the basis is this much only, right? Basis is this much only. So what is the basis? What is the answer? Okay, this is the basis. So null space contains just zero vector. Okay. So here in this case, null space contains just zero vector, which is fine. Okay. So see, if you want to solve this, you can say, since there is no free variable, right? So how to solve this? So see here, since there is no free variable, then you will be getting x equal to all zeros, right? All zeros. Yeah. So that is why basis for null space is just this much only, like 0 0 0. If someone asks you dimension of null space, then what is your answer? Dimension of null space? Yeah, 0, right? 0. Because if this is the only vector, then this dimension of this space is 0, right? This is important. Dimension of the null space is 0. Okay, it is not 1. I think yesterday itself we have defined it, right? For the 0 vector, dimension is just 0. Dimension of that space. Okay, because it is dimensionless. I mean, it is not 1D. Is this 1D? Is this 1D? Tell me, is this a 1D? It is just dimensionless, right? Okay, okay. So Aditya is saying, sir, how could 0 be the basis? Could you please explain? It's linearly independent set. Yeah, since it is linearly independent, then the only solution is trivial solution, right? Since it is linearly independent, there are three pivots, so only solution is trivial solution. So that's why this is the only solution here. How it is dependent? It is independent, right? Because these are the three pivots. Okay. Since these are the three pivots, that's why it is linearly independent. So these columns are linearly. No, this is dependent or independent doesn't really matter. Okay. I mean, this by default we call it basis. That's fine. I mean, we can call this basis. Okay. If this is the only zero vector, this you can consider the zero vector as an exception. Okay. For the basis, we can call this a zero dimensional basis. Okay. We can call this a zero dimensional basis. So you are saying that, okay, why we are calling this basis? Because we have zero vector here. Yeah, we have the zero vector, but you can consider this is by definition. Okay, we can have zero vector in the basis, and if zero vector is present, we call it zero dimensional basis. Okay, this is by definition we can have it. Okay, so how to find null space? How to find null space? Begin with the Gaussian elimination ax equal to 0. Look at the constant. I mean, you just solve ax equal to 0. So basically, right? Solve ax equal to 0. That's all. Okay. I mean, factor out, which means decomposition. You know decomposition, right? So decompose and these things. But yeah, that's fine. You just solve x equal to 0. Now, let's just do this interesting question, which is saying find the basis for the column space. Is this the same question? Okay. So let me just copy this. This is 1, 1, 0, 0, minus 1, 1. So you are getting 1, 1, 0, 0, minus 1, 1, 0, 0, 2 or minus 2. 2. Okay. So if you do the elementary operation, then the reduced form, you will be getting something like this. Now they are saying find the column space of A. Okay. Let me give you the options. Let me give you the options. Let me give you two options here. Okay. So for this question, let me give you two options. Option A and option B. The column space will be this span of this, because all of them are linearly independent. I mean, the basis for the column space, will it be this, or will it be this, or it doesn't really matter, or both are the basis? I mean, tell me. Both are the basis, or only A, only B, something like that? Just think about it. See, we found out that all of these three columns are linearly independent, right? Let me give you one example. Let me give you one example. Let's suppose this is the matrix that you have. Can you tell me the column space here? I mean, the basis for the column space. Can you tell me? Yeah, I think it is very easy. It is very easy. The basis, okay, I'm just asking the basis. It is 1, 0, isn't it? Okay. Now you do the row operation. Let's suppose you do R2. You're replacing this R2 by R2 plus R1. You do some row operation, and then you got something like this. Okay. Assume you got something like this. Can you tell me basis for this column space? See, the earlier column space that you were having is 1, 0, right? Earlier column space. Now you are doing some elementary row operation, and now I'm asking you what is the basis for this basis of this new matrix column space. So what is your answer here? It will be changed, right? So the will be basis here will be 1, 1, isn't it? And tell me, are these space same? Let's suppose I write it span. I write it span here. Is this space and this space same? Are these two space same? No, right? No. Okay. So what is happening here? What is happening here? You did elementary row operation. Just a second. You did elementary row operation, and after elementary row operation, we are getting different bases, right? So can you not do elementary row operation? So these two spaces are different, right? These two spaces are different. Okay. See, see, I'm asking you basis for this column space. You just told me this. Actually, this is correct. Okay. This is the correct answer. This is the correct answer. Now, just for the sake of curiosity, what I did the elementary row operation, and I got some new matrix, and now I'm asking basis for this new matrix column space. Okay, which is this? And actually the column space, I mean, has changed, right? So So we did elementary row operation and we found out the column space itself got changed, isn't it? So we did elementary row operation and we found out that column space got changed, right? So to solve the questions regarding the column space, can I not do elementary row operations? Which means if I'm doing this step and then I'm asking you what is the what is the column space of this particular matrix? Let's suppose something like this. If I'm doing this step and I'm asking you what is the column space, is this step wrong? Is this elementary row operation? Is this step wrong? Tell me. Should I not do elementary row operations? Because the column space is changing. We have just seen, right? See, we have seen that if you perform the elementary row operation, the column space got changed, isn't it? So, regarding whenever there is a column space question, can I not do elementary row operation? How many of you think I should not do elementary row operation? And how many of you think we should do? Because column space got changed, that is for sure. Okay, that is for sure. There is nothing wrong in this. We have just seen the counter example or the example, whatever you like to say. Okay, so there is the fact that we have established that if you do elementary row operation, then the column space will be changing. That is for sure. But here is one idea. You can still do elementary row operation and we can still get something from here. Okay, let me just tell you one thing. Let me just tell you one thing. How many of you have seen one lecture which is row reduced echelon form? Okay. So there in that lecture, I have told one very interesting thing. You do elementary row operation. Okay. You do elementary row operation and then you get something. Now let's suppose I get something like this 1000. Let's suppose I get something like this. Okay, can you tell me in this which columns are linearly independent, the column numbers? Can you tell me? I think this is the pivot, this is the pivot, and this is the pivot, right? So these three are pivot. Okay, so let me just mark the pivots. So these three are pivot. Can you say these three are linearly independent? Linearly independent, right? Linearly independent, linearly independent. Now, can anyone tell me the relationship? Okay, the relationship between let's suppose C3. Okay, let's suppose this is C1. Okay, this is C2. This is C3. This is C4. C3 and C1, C2. Can you tell me the relationship between C3 and C1, C2? Yes, extremely nice. So basically, the relationship doesn't change. Okay, how many of you know about this? That if you do elementary row operation, see यहाँ से देखने से we got to know that C3 or this column, the third column is linearly dependent on these two, which is A and 2B, right? So if this column is linearly dependent on these two, then this column is also having the same coefficients, and it is also linearly dependent on these two, isn't it? So basically, whatever is this column, I don't even know. Let's suppose I don't know. Okay. Whatever this column can be represented as a linear combination of these C1 and C2. I talked about it in the row reduced echelon form lecture. Okay. If you've not seen, just see that lecture. Just watch that lecture. So the important thing here that I want to establish is that okay, let's not worry about the column space, that it change, not change. Let's not worry about it. The important thing that I want you to recall is that the relationship between the column doesn't really change, right? Relationship or the linear dependency between the column is preserved, right? Linear dependency between columns is preserved, which means if these are linearly independent, right? If 1, 2, and 4 are linearly independent, then here also 1, 2, and 4 linearly independent, isn't it? समझ में आया? And what do you need for the basis? What do you need for the basis? You need linearly independent columns. See, can I say these four vectors are basis of column space? Tell me, can I say here that these four vectors are basis of column space? Obviously, no, right? So here, if we have something like this, then answer is no. Just tell me, can I say these four vectors span column space? This answer is yes. So if someone asks me that give us the columns which span column space, that's very easy, right? Okay, you just give these vectors, all of these vectors. But if someone asks me, really ask me the basis in which we are really interested, right? If they ask me the basis, how to find the basis of column space, this is the question. Okay, so this is the main question that I want to address in today's lecture, is that how to find basis of column space. Okay. See, I think one thing is clear to everyone, that how to find basis of null space, right? Is this okay to everyone? How to find basis of null space? At least instead of column space, if I write null, just solve Ax equal to 0, right? Okay. Just solve Ax equal to 0. You will get the basis of null space. Now let's just see how to find basis of column space. Okay. This is very interesting. What you will be doing is just tell me, are these set of steps correct or not? Okay. This is echelon form. Need not to be reduced one. Okay. This is row echelon form, normal row echelon form. From this row echelon form, get the pivots. Okay. So from this row echelon form or echelon form, whatever you would like to say. Okay. No linearly independent columns. And now here is the answer, that corresponding columns in the original matrix is basis of column space. Okay. Are basis of column space. Everyone understood this? Let me know. Basically, we will be applying the elementary row operations, but we will not be directly using row echelon form. We will be just getting to know that, okay, which are linearly independent. Once we get to know which are linearly independent, we will say the corresponding columns are the basis, isn't it? Isn't it a very nice trick that we are playing here? See, here you got to know that, okay, 1, 2, and 4 are linearly independent. Then tell me, is this column space? Is this column space? No, this is not the column space. So now can you tell me the column space here? Okay. Is this understood? This is the column space. Let me know. Let me know if there is any issue in understanding this. Okay. So what we will be doing, The column space is very interesting, that we will be basically doing the elementary row operation. Column space is getting changed. That's okay, because we are not using that space, right? We are not using directly the column space. We are just getting to know, okay, which are linearly independent and which are linearly dependent. And then we will go to the original matrix to tell the basis for the column space. How many of you are okay with this explanation? Obviously we will do at least, I mean, many examples, at least 10-15 examples we will be doing. For example, this, and there will be, I mean, many examples we will be doing. But even before the examples, is this okay? That what is the idea? So what we will do, we will take A, reduce it to R, get to know which are linearly dependent or linearly independent, and then we will go back to A. And these corresponding linearly independent columns are the column space, right? Are the basis for the column space. Okay. So now let's just do this question. Determine the basis for the column space of this. So obviously we need to reduce it. So I don't want to spend time in that. So that's why I have the, I mean, row reduce equivalent form here. Okay. Reduce row equivalent form is this. Okay. Now you just tell me, what is the column space. See, what are the linearly independent? This is there, this is there, this is there. So this is first, third, and fifth. So what is the column space or the basis for the column space? Which columns will be here? Let's suppose this is the column number E1, this is the column number E3, this is column number E5, this is column number A1, this is A3, A5. So what is the answer? Yeah, from A, right? So basically from A will be the answer. I hope everyone understood. So it will be 1230, right? -1, -1, -1, 1, and 0010. Actually, the column space is changed. So you can't directly take this. Okay. You can't directly take this. Okay. The column space is changed. But from here, we get the idea that which are linearly independent. And then I go here. Okay. Because the linearly dependency is not changed. The linear dependency is not changed. The column space will be changed. Understood? Okay. Now let's solve this question. What they're saying. Each question is worth 4. Suppose there is a matrix which got reduced to this. I think this is the previous one only, right? Okay, this is different. I think. Okay, that's not a problem. The null space of this A, is this true or false? The span of this. How many vectors should be there in the null space? I think only one vector, right? Okay, only one vector. You can just quickly verify whether multiplying this will get you 0 or not. -2 of this, -1 of this, and 1 of this. I think it is 0, right? Yeah. So it is true, right? Because this 2 1 is nothing but 2 times this and 1 time this. So you are already having this -2 and -1. So I think that's fine. So this is true because there is only one vector, and it should be of some form. So it doesn't really matter. You get just one vector, you multiply by the k. Okay. So it should be a span of any one vector. If you're getting, that's fine. Okay. So that's true. Column space is the span of these vectors. Tell me. This is true or false? So they are saying suppose 4 into 4, they are giving you row reduced to this. They are not giving the matrix, original matrix A. Okay. So the original matrix A is not given. They are saying that or row reduced to this. Then actually the original matrix was given in the question, but I forgot to copy that. But that's fine. Okay. I think the original matrix was given in this PDF, but that's fine. So now you tell me, will this always be true? No, right? See, this, they are taking this, and this column. Will this form the column space? No. Okay, may not be. I mean, if A is same as this, if A is exactly same as this, then yes, otherwise no. Right? So it is not always true. Right? So you can say not always true. Anubis is saying, will it be true if fourth row in the original matrix is also 0? No, it will be true only when the original matrix is exactly like this. Okay. Original matrix should be exactly like this. Okay, exactly. The fourth, I don't think only the row will matter. Okay, the columns will also matter. So the original matrix should exactly be like this. Otherwise, you can't say in general. Okay. False, the column space is the span of first, second, and fourth column of A, which could be almost anything. Understood? This is of A, which could be almost anything. Let me know if that is okay to everyone. Okay. Is this fine? Or should I explain this again? Okay. Now tell me the dimension of the null space here and the dimension of the column space here. Do you want to solve this question? Is this in the equivalent form? Let's just check pivot element after the. Yeah, it is in the equivalent form, right? It is already in the equivalent form. Okay. So it is given matrix in the row equivalent form. Now, if you solve this, then I think this is the pivot element. This is the pivot element. This is the pivot element. This is the pivot element, right? So the number of free variables are one, two, uh, three, right? So that is why nullity, oh sorry, the dimension of the null space, which is also actually called nullity. Okay, nullity is how much? Three. Okay. And how many linearly independent columns are there? I mean the pivot columns. So it is four, right? Four. So I think this is four, which is also called as rank. So here is very interesting relationship between the dimension of null space, which we call it nullity. It is actually the number of free variables, isn't it? Number of, okay, sorry, two is the pivot, not one. Yeah, that is fine. अच्छा, एक मिनट मैं okay, let me just circle two. Yeah, two is the pivot, not one. Yeah, that's true. Okay. So number of what is the dimension of null space? Is this okay if I say number of free variables? Don't you think in the null space the solution will be having number of free variables? If this is the three free variables, it will be the three decomposition, isn't it? So the dimension of the null space is number of free variables. It is fine. And dimension of the column space is nothing but basis of the linearly independent vectors, or linearly independent vector, because that will be forming the basis. So it is nothing but number of pivot variables, or number of, you can say number of pivot variables. So actually, dimension of this column space is rank, and dimension of null space is nullity, because nullity is number of free variables. Okay, is this fine? What I'm trying to say? Let me just go to the next page and let me try to explain this once more. What I'm trying to say. See here, if this is the matrix after row echelon form, tell me, if you just want to tell the dimension, do you really need to solve it, or can you directly tell me the dimension of null space? It will be number of free variables, isn't it? Why? Because if you solve this ax equal to 0, so jitne free variables honge, that kind of, decomposition will be like that, right? So it is number of free variables. So by directly seeing this, you can tell which is number of, if I just ask you the dimension, right? If I just only ask you the dimension, which is nothing but nullity, right? Which is nothing but nullity. Similarly, if I ask you what is the dimension of column space, then it is number of linearly independent columns, isn't it? which is number of pivot variables, which is nothing but rank, isn't it? So the dimension of null space and dimension of column space are nullity and rank. And do you remember this rank plus nullity equal to number of total columns? Do you remember this relationship? Do you remember this? That rank, how many of you remember? Plus nullity equal to total number of columns. Yeah, that's called rank nullity theorem, right? Okay, that's called rank nullity theorem. So from here, can I say, just tell me dimension of column space uh, in whatever way you want to write, dimension of column space plus dimension of null space equal to number of columns, let's suppose n, right? Where is m cross n matrix. Okay, m cross n matrix. Tell me this, okay? Both dimensions add up to n. Fine, right? Okay, okay. So don't worry, we will be doing more questions, but I'm just asking you if this is okay to everyone or not. Okay. So Devesh is saying it is fine. I think Pankaj is also fine. So Aditya, Anuvesh, Deep, Diksha, Guddu Kumar, okay, Kapish, Pankaj, Parth. Okay, it is fine, right? Great. Now, let's just solve this question. Describe the column spaces and null spaces. Describe in the sense find the basis. Okay. Can you do this question as an homework? Find the basis of the column space and null space. Find the basis of column space and null space. Find the basis of column space and null space. Can you do this question as an homework? Okay, just try doing this question as homework. Answer I don't have, but you can put the screenshot in the comment section, or maybe you can do one thing. Yeah, you can put the screenshot in the comment section of the annotated notes. Okay. Answer I don't have, so you can find out the answer and then take the photo. You can put that photo. I think this is easy question itself. ठीक है, डायरेक्टली भी कर सकते हैं. So you know this, right? So I think the column space will be these two bases. I mean, bases will be these two. Here these are dependent, so that's why you can say just one of them. Okay. Here the column space will be. Here the column space will be how much? I think these you take two linearly independent. This is dependent actually. You just take this. Just take this, right? So I think this is the column space here. Null space. You can find out the null space. I think here it will be just zero, and here it will be, I think, yeah, maybe minus 2 and 1. Minus 2 and 1, if you multiply by minus 2 and 1, I think it will be getting you 0, something like this, right? K into minus 2 and 1. So you can find out this, right? It is easy question only. Just try to do it. Okay, just let me know if this is true or false. This is a good question. Just let me know if this is true or false. Okay, so what they're saying, if rank of a equal to n, okay, uh, has only trivial solutions. So they are saying all the columns, actually all the columns are linearly independent. That is the only way to say that it is having trivial solution. It means all columns are linearly independent. In that case, I think null space of A will be just having 0. Yes, that's true. Okay. Right. It need not to be square or something. Okay. It need not to be square. It could be like the rectangle matrix also. That's fine. So which means that let's suppose it is having three linearly independent columns. Okay, but you may be having four rows. This is one row, another row. I mean, these are the four rows. Let's suppose there is no pivot here in the fourth row. That's fine. Okay. Anyway, so the square and these things are not required here. If it is having trivial solution, it means the columns are linearly independent. It means that if it is having trivial solution, the only solution is trivial solution. So for x equal to 0. So actually they're telling you that what is the solution of x equal to 0, which means x equal to 0 is the only solution, right? It means the null space is containing only 0. So that's very easy. Okay. So can you do this question also as a homework? Find the null space and these things. I think answer on the next page. Okay. How many basis vectors are needed? Do you want to solve this as a homework? Answer will be on the next page. Okay, answers are not. Uh, yeah, that's easy only. You can do. So here, I think this is a multiple of 2. This is a multiple of 3. This is a multiple of 4. Okay, so only one linearly independent vectors are here. So basically, all of these vectors will be 0, right? All of these, I mean, there is no pivot here. So the only pivot you will be finding is this one, right? And all of this will be 0. So you can try solving this question. Okay. Similarly, this question also, just try solving these two questions. Answer is on the next page. Okay. Is this fine? Or should I solve? See, if you try, then it will be better for you only. Okay. It will be better. Answer is on the next page. So that's why I'm just saying that you can try. Let's solve this question. What they're saying. Uh, which of the following are subspaces of R4? Okay. They're saying subspaces of R4 and Y. Okay. Is this a subspace? I think yes, right? Linear combination of some vectors is basically the subspace. So I think A is the answer. This is actually MSQ question. A is the answer. What about B? Null space of this matrix. It is basically 4 into 3. So null space will be actually 3 into something, right? 3 into 1. I mean, null space will be having 3 dimensions. So can it be the subspace of R4? Is this possible if the vector is just having 3 dimensions? Sorry, it is 4 rows and 3 columns. Yeah. Tell me. So here, null space vectors will be having 3 dimensions, right? So in that case, can it be the subspace of R4? No, right? First of all, it has to be the subset of R4. Obviously, it cannot be the subset of R4. So that's why no. The column space of this, what do you think? Obviously, yes, right? Column space will be the subspace of R4. What about this? What about this? It is tricky. XY and YZ are equal. What about this? Okay, this is not a subspace. Let's just see why. Okay, so here XY and ZW, right? It was, yeah. So the multiplication of these two and multiplication of these two are equal. So for example, if you take these two vectors where the multiplication of these two and multiplication of these two is giving 0, these two vectors are in the vector space. But if you do the summation, it is not in the vector space. Okay. So I mean, some kind of these things are actually where they play some trick or something. Generally, they are not vector space. Okay. So this is not the vector space. You need to come up with the counter example. Okay. So generally, they are not vector space. So the counterexample here is that here we are saying xy and yz are equal. Sorry, zw. So this is x. Let's suppose these are the two vectors, right? I want to check whether the addition will also be following the same property or not. It need not to be, right? So you can even have anything. Let's suppose it is AB, it is BA. Okay. Here it is CD, it is also CD. So it will be A plus C, it will be B plus D, it will be B plus C, it will be A plus D. If you multiply these two, it is B plus C, it is A plus D. And if you multiply these two, will they be equal? No, right? So this is not in vector space. It is not in space. What is that space name? V. Okay. Priyanshu is asking, sir, after buying Gate plus DA course, will I get weekly quizzes as well as practice material? Yes, you will be getting everything that is there in the Gate CSE plus DA. You are saying like combo package you want to buy. Yes, you will be getting everything that is there in the CSE that is there in the DA. Okay. So there is a like two more spaces, which is row space and left null space. So we have seen column space, right, of A, which means whatever this is forming is, I mean, these columns, whatever space they are spanning, this is the column space of A. We have seen the null space of A also, right? Now there are two more spaces of A, or if you want, you can call it that two more spaces that we can study, but they will be corresponding to A transpose. Okay. So which means that that if I have A transpose columns, okay, a column space of A transpose is basically nothing but the row space of A. Okay, we will see that later on. And this is called null space. Okay, null space of A transpose, we call it left null space of A. So actually it is I will tell you, but it is nothing but it is nothing but column space only of A transpose. It is nothing but null space only of A transpose actually. Okay. So basically mainly there are only two spaces. What are those two spaces? Column space and null space. We can transpose the matrix and we can talk about their column space and null space. Their column space and null space are called row space and left null space. Okay. I mean, we will talk about it, but I'm just telling you the terminology here. So what are the two, main spaces? Column space and null space. And how they are related? Using rank nullity theorem, right? Rank nullity theorem. So basically, there are only two spaces which are related by rank nullity theorem. You can take the transpose of the matrix. You can talk about the column space of A transpose, which is nothing but the row space of A. You can talk about the null space of A transpose. We call it, I mean, there is just one name which we call it left null space of A transpose. Sorry, left null space, yeah, left null space of A. Okay. Anyway, so we will talk about it. Now, just tell me, should I talk about it today or tomorrow? If it is going too heavy, we can talk about it tomorrow also. Just let me know, because since the session is just started, and if you want, we can go or the at the slow pace currently, because I know there is a buffer. Okay, I know there is a buffer. There is too much buffer we have already kept. Okay. So maybe it will take some time, maybe 1.5 more hours. So it is better if I do it in the tomorrow's lecture. Okay. ठीक है. And then we will solve questions like this. Ki find the basis for the all. These are called four spaces. Okay, I mean the left sorry, the null space, column space of A, and null space and column space of A transpose. Okay, or you can call it row space and left null space of A. Anyway, so basically we will find the basis of all of these four spaces. Okay, I mean we will do question like this later on, and then we will find those bases, and then we will do many other questions. Okay, we will do many other questions, true false question and these things. Cool. ठीक है. Okay, ठीक है. So thank you everyone. Thank you for joining in. Tomorrow we will start this topic, right? Tomorrow we can start this topic, which is this one, which is also very important. Okay. And then once you understand all of these four spaces, then we will relate all of these four spaces very nicely. Okay. Using some geometrical diagram, we will relate all of these four spaces. And actually, the diagram that I will tell you that how they are related. That diagram is the the cover page of the book, like the cover page, okay, of some book. So that diagram is printed on the cover page of Gilbert Stein book. Okay, that diagram is so popular. So we will relate all of these four spaces because the relation is very interesting. Okay. Thank you, everyone. Thank you. Take care. Bye bye.